Okay, let's wrap up chapter 10. We're going to talk about using our T procedures wisely and connect back to something we did quite a long time ago and how that might be confusing with what we're doing now. So, hopefully, we'll eliminate any confusion before it sets in. Okay, so when doing two sample T procedures, remember that's when we're doing the confidence interval, or a test of significance for means. Should we pool the data to estimate a common standard deviation? Is there any benefit? Are there any risks? So when we're doing a T procedure, we do not pool. Always choose no on the calculator. Pooling data assumes that the variances are equal. This is an incredibly special case. That means it'll happen, but not very often. So we will not pool because it's not in the scope of our course to actually know that the variances are equal. The benefit of not pooling the data is we'll have a slightly better power due to a larger degrees of freedom. The risks would come if the equal variance condition is not met, but we pooled anyway, and then the p-value is going to be way off. So, bottom line, when you are doing the T procedure in your calculator, you are not pooling your data. So click no, or don't unclick it because the default setting is no. So what about a two sample test for a difference in proportions? Why do we pool for this test? So always pool for proportions. Remember PP? It gives us more accuracy because a single value of p hat gives us the best estimation of the standard deviation. Instead of using two different p hats, we combine them and get one single value of p hat. And remember, we're pooling because in a test for a difference of proportions, the assumption is that P1 is going to equal P2. So we are able to pool in that scenario. So again, do not pool for T procedures, pool for proportions. All right, so this is where I want to spend the heart of today. Should you use two sample T procedures with paired data? So before I get into this, let me remind you, paired data, which we learned back in chapter 4 when we were talking about how to set up ways to conduct experiments and collect samples. Paired data would be, let's say, if we were together and we were going to do pool noodle javelin, this would be where my pool noodle javelin activity would come in. And the idea would be, do you throw a pool noodle further with your dominant hand versus your non-dominant hand? So if you're right-handed, the assumption would be that you would throw further with your right hand than you would with your left hand, and vice versa if you were left-handed. So we would run a test of significance on this data. But because you are given both treatments, that would be considered to be paired data. So we would have flipped a coin to decide which arm you throw with first. We'd measure the distances and we'd see if there was a difference in the left hand's length that was thrown in the right hand's. So in a way, it's like we have two samples, but we really don't because each person has two pieces of data. It's not really two samples. The data is paired together. So although when you read it, a problem like this, and you'll see in just a minute, the thought might be, hey, this is two sample, but it's not. And we've done problems with paired data, but that was before we knew about these two sample procedures. And it's very common for kids to get the two sample procedures, to use two sample procedures on paired data. So the rest of this video is going to talk about how to avoid using two sample procedures when it's supposed to be paired data. Okay, so should you use two sample procedures with paired data? No. If the data is paired, it needs to be treated as a single sample. Therefore, it would be appropriate to use a one sample t-test for means/proportions, depending on whatever you are doing. And one way you can know if the procedure, which procedure to use is if you think about it, if you scramble your data in one of the lists and it causes your data to get all messed up, then the data has been paired. So in each of these following settings, we're going to decide whether we're going to use a 2-sample T procedure, or if we're going to use a paired T procedure. So before exiting the water, scuba divers remove their fins. A maker of scuba equipment advertises a new style of fins that is supposed to be faster to remove. A consumer advocacy group suspects that the time to remove the new fins may be no different than the time required to remove the old fins on average. 20 experienced scuba divers were recruited to test the new fins. Each diver flips a coin to determine if they wear the new fin on the left foot and the old fin on the right foot, or vice versa. The time to remove each type of fin is recorded for every diver. So ask yourself a question. Is this a 1-sample scenario or a 2-sample scenario? And for me, I like to start with the 2 samples. Do you have 2 distinct samples? And the answer here is no. It may feel like you have 2 distinct samples because you've got old fins and new fins, but because we are putting one of each on a single person and timing how long it takes them to remove the old or the new, then the best scenario would be to keep those 2 numbers together, pair them, and subtract to find if the old fins take longer than the new fins. So this is going to be paired data. So we're going to use a paired T procedure. Now remember, so if you were to list the times for the divers and you were to scramble up the times for the removal of the old fin, then it wouldn't match because it would lose where it wouldn't be beside the person who actually performed the taking off of the fin. So this is paired data. So look and see, do you have 2 separate samples, or is it really just 1 sample because you've paired the data? All right, to study the health of aquatic life, scientists gathered a random sample of 60 white piranha fish from a tributary of the Amazon River during 1 year. The average length of these fish was compared to a random sample of 82 white piranha from the same tributary a decade ago. Now, I hope you can see you have 2 distinct samples. You have the sample from a year, or the white piranha from 1 year, and then the white piranha from a decade ago. So these are 2 distinct, completely different samples. So you would use a 2-sample t-test for means. Because we're doing the average length, so that would mean we're doing means. All right, can a wetsuit deter? Hang on, let me get me some room down here so I can write. All right, so can a wetsuit deter shark attacks? The researcher has designed a new wetsuit with color variations that are suspected to deter shark attacks. To test this idea, she fills 2 identical drums with bait and covers one in the standard black neoprene wetsuit and the other in the new suit. Over a period of 1 week, she selects 16 2-hour time periods and randomly assigns 8 of them to the drum in the black wetsuit. The other 8 are assigned to the drum with the new suit. During each time period, the appropriate drum is submerged in waters that sharks frequent, and the number of times a shark bites the drum is recorded. Please press pause. Think about this. Is this an example of paired data or 2 samples of data? All right, so this is 2-sample. This is an example of 2 samples. So we're going to do a 2-sample t-test for means. So this data was not paired. So we do have 2 groups. So we have 8 groups of the black wetsuit. That's one of our samples. And we have 8 groups of the new wetsuit, even though the 8 different times would consist of your sample. So that would be a 2-sample t-test for means in that scenario. So the next 2 problems we're going to do, we're actually going to work 2 problems, as you might would see on your exam, and talk about the subtle differences between paired data and 2-sample T procedures. Researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. For one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which the subjects took caffeine and the placebo was randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression at the alpha equals 0.05 significance level. The table below contains the data on the subjects' scores on the depression test. Higher scores show more symptoms of depression. Construct and interpret a 90% confidence interval for the true mean difference in depression test scores, caffeine minus placebo. Okay, so we want to estimate mu, the mean depression test score for caffeine, and the mean depression test score for the placebo group. We want to subtract these to see if caffeine makes a difference. And so we're going to estimate mu sub C for caffeine minus mu sub P for placebo at the 90%. Oh, wait, hang on. You know what I just realized? I realized that this was 2 questions. Okay, I'm gonna pause this real quick, get my head on straight, and then I'll be back. Okay, so the spacing on my document messed me up. So there was actually 2 problems here. We were to do the test at the alpha equals 0.05 level, and we're going to do the one for the confidence interval. So I went ahead and wrote some stuff down just to save some time. We're going to let mu sub C be the true mean depression test scores for the caffeine drinkers, and mu sub P be the true mean depression test scores for all non-caffeine drinkers. Remember, one of the errors that students make when describing experiments and defining the parameters is they make the parameters appear to be talking about the 2 samples. So you want to make sure you use language like for all caffeine drinkers, for all non-caffeine drinkers. Don't say things like the true mean depression test scores for those who drank caffeine, because then that implies that you're discussing the sample and not the population. And parameters have to describe a number for the entire population of caffeine drinkers. So make sure that your language is clear when you are defining your variables in an experiment. All right, so we have our null hypothesis is that mu sub C, the mean for the caffeine drinkers, is going to equal the mean of the placebo. And your alternative, I think I was wrong. So let's see if we can figure this out. I should not have used not equal to. I was writing very quickly. Let's see. We want to know, researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. All right. So if we are going to deprive us of caffeine, and it's going to lead to an increase in depression. So that means the mean would be greater than the placebo group. So if we don't have caffeine, we would have greater depression. Wait, I think I did that wrong. Let's think about this again. And you're probably yelling at your screen, which I hope you are. That would make me happy. All right. if we take away caffeine, we would have a higher depression rating. So I wrote it the wrong way. So we're going to put greater than. So the caffeine group scores would be less than the placebo group score. And we got the alpha equals 0.05 level. I went ahead and checked the conditions. The random condition has been met because the treatments were randomly assigned. Remember, we don't always need to say a simple random sample because, in honesty, this is not a simple random sample, but the random assignment of treatments ensures that the random condition has been met. The independent condition, we do have two groups that are independent of each other. We actually don't have two groups that are independent of each other because we just have one group. But random assignment ensures independence. So I'm going to scroll back up, make sure you know what I'm talking about. Each subject didn't drink caffeine and took the capsules. And then the subject, it was the same subject for both treatments. So we only had one group of people. So random assignment ensures independence. Check. We do not check the 10% condition because this is an experiment. The normal condition N is less than 30, so we're going to have to check our graphs. So I'm going to go over here to the calculator now. I have entered in the data into list 1 and list 2. But before I do any graphing or anything, let's talk about, is this a 2-sample procedure or is this a paired procedure? Well, I hope that you can see that this is a paired procedure. We are going to need to actually subtract the 2 scores for each person, and we're only going to look at the differences in their 2 scores. So we are looking at one sample of the differences. So I'm going to come over here to L3, and I'm going to find the differences. Well, the problem said to do the caffeine group minus the placebo group, and I put the caffeine group in list 1, and I put the placebo group in list 2. So I'm going to highlight L3, and I'm going to find the differences between L1 minus L2. So here we have the differences. So I'm going to talk about, make sure you understand what this data is saying. So this person scored a 5 when he or she drank caffeine, but then scored a 16 when they did not have caffeine. So the difference is -11. So that means that their depression was scored worse or higher, a higher rate of depression in the placebo group because the score is negative. This is a paired t-test because we are only going to be looking at list 3 as our one sample of data. We're going to run the test on the differences. Okay, so back to the conditions. We need to check that the differences, the graph of the differences. So I need to do a histogram on L3 and analyze it for skewness and for potential outliers. And that does not look very skewed at all, and it doesn't have any extreme outliers. So for the interest of time, you know, on your exam, you're going to want to draw or sketch the graphs as best and as accurately as you possibly can, but I'm going to just write no extreme skewness or outliers. So our normal condition has been checked. It is safe to proceed. So we're going to do a paired t-test. This is otherwise known as a one sample t-test. Remember, we're only doing the one column for the differences. So go back to your calculator, and I'm going to do stat over to tests. I'm doing a one sample t-test. That is number 2. So we're going to have our data. Our null hypothesis is 0. And I'll come back over here and remind you. If you do m mu sub c minus mu sub p, the difference between these two is equal to 0. If the caffeine really doesn't make a difference and the depression rates are the same for both groups, then the difference would be 0. So that's why we have 0 in as our default. This can change, but we're going to just let it be 0. For this example, it is 0. But this time we're going to run our test on list 3 because we're running our test on the differences. And our null hypothesis was less than. So we're going to calculate. So with our tests, when we do the do step in the calculator, we need to write down our t-test statistics. Our t-test statistic is negative 2.75. And our p-value is 0.01. And just to, like impress your grader, you could also draw and put negative 2.75 less than, so that is 0.01. Anyway, that's, and then we also need our, don't we need degrees of freedom? Oh yeah, we need degrees of freedom, but we can do that quite easily. I was thinking the calculator told us, but it's easy to do with one sample. It's 2 samples that the degrees of freedom is that gross ugly formula. So our degrees of freedom is our sample size minus 1. Our degrees of freedom are 10. So since our p-value of 0.01 is less than our alpha level 0.05, we reject the null hypothesis. We have convincing evidence that not having caffeine increases depression. All right, and then it wants us to construct and interpret a 90% confidence interval for the true mean. So we're going to estimate the difference in the 2 mean depression scores, which we already defined up top, so we don't have to define them again. And we're going to do it at the 90% confidence interval. So that's the state step. The conditions are the same, so we check those above. We don't need to check them again. And so we're going to go and do a 1 sample t interval. Or you could do a paired, both of these are right, t interval. Okay, so let's go find that on our calculator. So stat, calculate, we're going to do, over to test. We're going to do a 1 sample t interval. So number 5 is a 1 sample test for proportions. So there, number 8, when it just has 1, no, the number 2 is not in front of it. It means a 1 sample t interval. Press enter. We do have our data in the calculator. We are still running the interval on list 3, the differences. This time it asked us for a 90% confidence interval. So I'm going to change that 9 to a 0. Calculate. So our confidence interval is negative 9.05 to negative 1.86. Negative 9.05 to negative 1.86. So we are 90%. Oh yeah, degrees of freedom is 10 still. We are 90% confident that the interval from negative 0.05 to negative 1.86 captures the true average difference in depression scores. I'll say it again in case you're writing. We are 90% confident that the interval from negative 9.05 to negative 1.86 will capture the true average difference in depression scores. So just real quick, notice that all of those numbers are negative. So the entire interval is below 0. So that will further support our decision to reject the null. That one of the plausible values at the 90% level is not 0. So that's supportive right there. All right. So does memory training help? Let's do another example just to make sure. I'm not going to do all of it out in its entirety. I feel like I've done enough of those, but we'll just kind of do the mechanics and discuss everything that needs to be written down. Does memory training help? Subjects will be given a list of words. They will be given 3 minutes to memorize as many as possible by just rereading the words. They will record as many words as they can remember. Subjects will then be given another list of words to memorize for 3 minutes using a memorization strategy. Now, I hope you can already tell that this is going to be another paired t-test. So, because you've got each subject will be performing both strategies. So they will record. Anyway, suppose that 32 seniors were randomly selected to try both memory strategies. Each student calculated the difference in the number of words that they remembered, strategy 1 minus strategy 2. The mean of the differences and the standard deviation, all that is given there. Do these data give convincing evidence that strategy 2 improves the memory at the alpha equals 0.05 level? All right, so let's write our null and our alternative. Now, I'm not going to define the parameters and all that good stuff because y'all are getting tired of hearing me talk, and we'll get through this as quickly as we possibly can, covering everything. All right, so I'm going to use a different notation because we've already decided that this is a paired test because each subject's getting both are using both strategies. So what we could do instead of doing the mu of strategy 2 minus the mu of strategy 1, I could say the mu of the difference because we are just looking at that one column of numbers after we subtract the two number of words that they remember. So you could use mu sub difference, and that would just ease up your life a little bit. And then you would say mu sub difference is the true mean difference in number of words that are remembered when we take strategy 2 subtracting strategy 1, and then you don't have to write two different parameters. All right, so mu difference, this is going to be greater than 0 because it says, do these data give convincing evidence that strategy 2 improves memory? Well, since we took strategy 2 and subtracted strategy 1, if strategy 2 improved memory, that means that more words would be remembered using strategy 2. So the first number will always be bigger than the strategy 1 number if strategy 2 is more effective. So when you subtract a big number minus a small number, your answers will always be positive. So your mean difference will be greater than 0. All right, random. The subjects were randomly selected, and I'm a little bit concerned about our conditions here because the random condition has been met because the 32 seniors were randomly selected. But this was an experiment, and was the treatment randomly assigned? I think I would need more information to be 100% certain that the random condition was met. And if you saw a problem like this on your AP exam, you would write exactly what I just said. And then say some little caveat, we will proceed with caution because they're not going to ask you to do a test if they don't want you to actually do the test. So comment on why you think the condition may not be satisfied, but then proceed. And that also, independence. This is an experiment, so I really don't want to check the 10% condition, but I'm not sure if the random assignment. Okay, so the independent condition would be met if the treatments were randomly assigned, and you would stop there. But since we don't know that, then I'm going to check the 10% condition. And let's assume that the school, or that there are more than 320 seniors out there in the world. So the 10% condition would be met. And then we're checking the normal condition, and that n is greater than 30. Yay! So by the central limit theorem, we don't have to do any graphing. So the normal condition has been met since the sample size is larger than 30 by the central limit theorem. We are going to do a paired t-test, or you can say a one sample t-test on the differences. All right. Stat over to test, a one sample t-test. This time we don't have our data, we have our statistics. Mu is still going to be 0. X bar was 1.5. The standard deviation of the difference is 2.77. Oops, click the wrong button, 2.77. Your degrees of freedom, we had 32 in our sample size, so the degrees of freedom, oh wait, that's not degrees of freedom, that's n. Degrees of freedom will be found later, it's 31. And then our our alternative hypothesis was greater than. Enter. Calculate. All right, so our test statistic is 3.06. So t equals 3.06. Our p-value was 0.002. So we have significant evidence to, hang on a second. All right, so since our p-value is less than our alpha level, 0.002 is less than 0.05, we will reject the null hypothesis. We have convincing evidence that strategy 2 improves memory. Then the next question asks, somewhere down here, well, there was another question I thought. Anyway, I guess not. So that's it. One more video and we are done.